Alrighty. So today we're going to kind of finish off our discussion of environmental chemistry. We have a few more things to talk about with regards to like water purification, and then we'll just talk about green chemistry for a bit. Relax, and then we'll be done for the day. So it'll probably be a pretty short one today, but I'm not going to start thermodynamics. I mean, there's really no point given you have an exam next week, and I don't want to put new stuff out there. So, anyways, with that, last time we saw that we can treat water to kill bacteria and viruses. And so we kind of use two agents. There's kind of two different agents that are commonly used. One of them is bleach, which actually comes from a reaction of chlorine gas or chlorine liquid with water to make hypochlorous acid and hydrochloric acid. As you know, bleach is an oxidizing agent. It is very good at doing that. That's why if you spill bleach on your clothes, it oxidizes the colors away and you're left with kind of that white spot. It's also very, very good at killing things because when things get oxidized, they die. So it's a pretty potent oxidizing agent. And as we've seen, ozone is also an oxidizing agent. That being said, chlorine is cheaper, but there are problems associated with it. So this one is cheaper, but this is problematic if it were to encounter other things. Primarily, if it encounters the bromide ion, we're going to see that this will actually oxidize the bromide ion into forming hydrobromic acid, hypobromous acid, my goodness, and the chloride ion. And these two things can react with things like methane in the water. So there are, or just kind of just generic hydrocarbons. Just using methane in this case for any small amount of methane in there. And that can create various halomethanes, which are going to be particularly nasty. You can keep kind of going on, keep throwing more bromines on there. Can totally happen. All of these are very bad things. It's going to be the same with the chlorination. This can form etc. So we can get all these sorts of halogenated hydrocarbons out there. And guess what? These guys, all of these, fly off into the atmosphere and kill the ozone. So we saw last time that we had CCl bonds that were weak enough that the light would break them apart, forming chlorine radicals. Those chlorine radicals act as a catalyst in the decomposition of ozone. Bromine radicals are going to react the same way. So unfortunately, if these are present in your water supply, using chlorine as an oxidizing agent can have nasty effects as these things are released into the atmosphere as a result. And so bad things can happen there. Unfortunately, there's kind of not really an economical way to purify the water, so it's kind of just a matter of using as little chlorine as possible, just to avoid any of these kind of side reactions from happening. And then there's also the idea that the longer or more thoroughly you can aerate your water before you purify it, the more likely you are to just boil off the methane or whatever organic compounds are there so that they're not present to react with any hypochlorous acid or whatever happens to be there. So, similar idea here. Ozone, of course, can be used, is still problematic though. Notably, it will react with the bromide ion. To make our delightful hypobromous acid. And then it can react with it again to form the bromate ion. And that's problematic for a number of reasons. We probably also get oxygen in this as well, maybe. Yeah, I think if we want to balance things out. Yeah. Yeah. And so the problem here is, of course, bromate is an even stronger oxidizing agent. It's also very toxic. And it's non-volatile. So this stays in your water, and people drink it, and bad things happen. And so ozone, being a stronger oxidizing agent, can cause bromates to form. Those are not good in your water supply. So even using ozone can still have some unwanted side effects from killing all of the nasties in your water. So again here, the best solution is to just kind of use as little as possible. Ideally, if it were feasible, something like UV would be a good way to sterilize the water, but just kind of the amounts that you'd need and the power that you need just kind of make it not as useful. So, yeah, sad things. So anyways, there's not really a super happy solution to purifying water, but it's just kind of doing the best you can. So it's just like in COVID life, right? There's no solution, but we just do what we can. Alrighty, so those are the problems with that. Let's talk about green chemistry. According to our book, that green chemistry is going to be kind of just environmentally conscious chemistry. And this kind of applies more to industrial things as well as kind of research in chemistry, drug design and producing industrial chemicals. The more we can kind of make them greener, the less they impact the environment in a negative way. And it's really just a set of principles. And our book outlines 12 of them. And by no means should you memorize these. I don't know them all, so I'll be just copying them out of our book here. So our first one is prevention. So we don't want to use things that we don't need to use. So we kind of just want to prevent making toxic byproducts. We want to prevent using extremely explosive things. It's kind of, just our catch-all for avoiding nasty stuff. So kind of just avoid waste in general is going to be kind of one of our principles here. Our next one is atom economy. Oops. My goodness. And this principle says that we should incorporate as many atoms from our reactants into the desired product as possible. So we don't want to use, 16 different reactants to make one product that, most of those reactants don't even figure into the product. We'll see some examples of atom economy later. We want to kind of avoid making waste. That's the idea here. So the more atoms we can integrate into our final molecule, avoiding waste products, that's going to be the atom economy side of things. Next one we have is just having less hazardous syntheses. And so that just means using safer solvents, using safer reactants, so ones that are not extremely explosive, or ones that require a glove box, or, special handling. So just kind of the, if we have safer alternatives that will get the job done, particularly with oxidizing agents. There was a lot of research going into oxidizing agents that are going to be less harmful than things like peroxides, or some nitric acid, or bromates, or that sort of thing. So less hazardous syntheses are nice. Designing safer chemicals. So maybe choosing ones that maybe are not, that can get the job done without incorporating toxic elements into them, or just kind of, if you can design them in such a way that you're going to minimize any nasty side effects that could happen if they're introduced into the environment. So just kind of keeping these things in mind there. There are 12 of these, as I've mentioned. Safer solvents. So perhaps you've seen television at some point in your life. And perhaps, or you've heard about meth labs exploding. That's a problem of solvents. So many solvents are volatile organic compounds that are very flammable. And so kind of minimizing their use, is ideal. And some solvents are also extremely toxic, like benzene is highly carcinogenic. Dimethylformamide is also carcinogenic. And these are, DMSO will drag things through your skin. So we want to avoid using kind of more toxic or explosive solvents when we can. So using water as a solvent, if possible, is a great idea. Water is a very safe solvent to use. All right. Energy efficiency. So if you can get things to happen using less energy, of course that's a better thing, because that means we don't need to burn as much coal or whatever to get that energy in the first place. So there's some effects that way. Renewable feedstocks. So that means choosing starting materials that are easily found, or ideally can be made from biological organisms. We're going to see in one of the examples of green chemistry later that using methanol instead of ethane in one particular synthesis is much better, because methanol can be produced by bacteria, yeast, and all that sort of thing, which makes it very easy to make. Versus something that we would have to go and spend a lot of energy and cost trying to capture or isolate as a compound. Especially something like ethane, where it's a hydrocarbon. Those are in limited supply as it is anyway. The reduction of derivatives. So with the reduction of derivatives, we want to kind of avoid having things that can undergo side reactions. So we kind of minimize the amount of steps that are going to be present in our synthesis, because that's going to get rid of intermediates that could react to form waste products. So again, this is all just going into reducing the amount of waste that we produce. So designing your synthesis that it's not going to produce as many intermediates there. What else do we have? Catalysis, of course. Catalysis, as we know, will lower the activation energy, allowing things to happen at lower temperatures. Very often, if you can recover your catalyst at the end of the reaction, that's great, because then you can keep reusing it and you can keep knocking down energy barriers for your particular reaction. Where are we now? Designing for degradation. So if your byproducts are going to end up in the environment anyway, if you can design them such that they will degrade more easily, that again will prevent the accumulation of waste. So having things that can be broken down by the environment is ideal. 2 more to go. We have just analysis. So we kind of just are, as scientists, we should always be taking a look at how our things can be affecting the environment. And so we should always be, critiquing our syntheses and procedures to say, hey, is this stuff ending up in the atmosphere or the rivers or whatever? What can we do? And doing that kind of constantly. So you're not just, let's once a year look at it, but let's look at it every day, see, is this better than yesterday? Have we improved our processes? And the last one is just safer chemistry in general. So, following safe practices, again, kind of avoiding explosions, because that's going to release stuff into the environment. Not dumping things down the drain when they should be put into waste containers. So just kind of safer chemistry in general. Ooh, that was an exhaustive list there. Any questions on any of those before we look at a couple of examples? So a lot of your homework is focusing on how you're applying these particular principles to various situations. So it's going to be kind of open-ended. You'll be able to see how to use some of these principles in your homework problems. All right, so here's an example. This is again from our book. We have benzene plus ethylene. And we're going to put this in some crazy catalysis procedure. I think they use an acid. I guess I'll use carbons. Oh my goodness. And then we can oxidize it to make styrene. Styrene is important because polystyrene is a... Here, you know what? I'll fix this one too. Hold on, let me move this back then. Styrene is a very important polymer. Polystyrene is. We use it all the time for a lot of different applications. Oh my gosh. Okay. And so we have some problems here. Benzene, extremely toxic. And kind of hard to come by. Ethylene is a gas that is a hydrocarbon. Well, both of these are hydrocarbons. And they're kind of hard to isolate. And so overall, they're pretty expensive in general. And kind of labor intensive. Not only if you're working with benzene, do you have to have a lot more safety materials around, but it's just kind of best to avoid it. It's kind of one of the most commonly known carcinogens. So a greener alternative is to use methanol instead and toluene. So toluene is a benzene that has an extra carbon on it. It is a hormone produced by plants for sure, But if you're going to try and produce, megagrams of polystyrene or styrene here, putting bags around plants may not be the most time or time. It takes a long time. That's what I'm trying to say. And then you would still have to isolate it and do all that stuff. So it's definitely a hormone that has plants ripen or fruits ripen and all that sort of thing. But in the amounts that it's produced, it's not really feasible to just harvest it from gases nearby plants. So we use toluene and methanol instead. And so I think what kind of catalyst do we use here? We just use a kind of a base catalyst. They use some sort of catalyst here. And you end up with your styrene molecule. And so there's a couple of important distinctions between these reactions. So notice that this one is 2 steps instead of 3. And as we can imagine, that's going to be probably the most or the most obvious one would be point number 8 here, the reduction of derivatives. So we don't want to have a lot of intermediates. We want to kind of, streamline stuff as much as possible. So this kind of deals with, what are we going to call these? Kind of number 8, whatever, principle number 8. So we're reducing our intermediates here. We're also going to be using kind of safer reagents. So that's going to be less hazardous syntheses here. So toluene is safer than benzene. So that's going to be, what number is that? Which one is less hazardous? Number 3. And I guess number 12 too. So just using safer choices. So we're going to be using some of these principles here. Methanol is produced biologically in volumes and is a liquid, so it's going to be easier to deal with. So while, yes, ethylene is produced by plants, that's not where it's isolated for industrial purposes. Just the amount is not worth it. It's already part of, natural gas as it is, so it's just kind of easier and more economical to just separate it from the natural gas. And so we're going to see that the fact that methanol is produced by bioorganisms, we can just dump in some waste, put some bacteria in, have the bacteria eat it, and produce methanol. Hooray. There we go. And it's also a pretty safe solvent, as is toluene. They're both safer solvents. But we don't really need a solvent this time. And then the last one is catalysis. It's just we're using a catalyst here, and that is going to be number 9. So in just a few ways, we can see how this kind of second route to making the same product is going to be more green than the first one for just a number of reasons here. And I'm sure you could make an argument for some of these other reasons as well, but these are kind of some big obvious ones for us. All right, let's look at another one. This is also from our book. This is for making hydroquinone. Oh my goodness, this is a long synthesis. But previously, here we go. Hydroquinone synthesis. We use aniline, 2 of these, some manganese, manganese 4, plus some sulfuric acid. As a result, we get our product of interest, which is the hydroquinone. That's that first molecule there. Actually, that's just quinone. It is not yet hydroquinone. We also end up making ammonium sulfate plus manganese sulfate, manganese 2 sulfate, plus water, 4 waters. And then after that, we're going to take our quinone and use an iron and HCl catalyst to reduce it to quinone, hydroquinone, sorry, which is our desired product. Okay, so this is our desired product here. Happy things. But notice we have a couple of problems here. We make 3 compounds that are not integrated into our final product. This is an atom economy issue. Notice we have all these extra byproducts that we're going to have to deal with. Transition metals are toxic to the environment. We don't want to use them, as much as possible. Notice we also are using sulfuric acid, which can be pretty hazardous in this reaction. And so this is tough. There's a lot of problems with this one. So a greener alternative will be to use I think there's an OH on there, yeah. We can just use this to split itself up. We end up getting a phenol off of this. Oh my goodness. And what's interesting here is now if we take this product that we made, the second step here, if we take that and add hydrogen peroxide, we end up getting our desired product. Same product as before, and we get acetone out. And what's interesting with this is if we take these guys, we end up with our starting material. Again, let's see. Yeah, there we go. So, go away. Notice, if we just look at our reaction here, let's see why this is a more green example. So, we are going to end up with side product 1, side product 2, but we put those together and we end up making our starting material again. So we're not going to end up wasting these. We can just isolate them and use them to do the process over again. And as a result, we don't have any waste here. We end up making our ideal product. Notice we had all of these transition metal wastes here, various salts that we don't want. We had to use toxic sulfuric acid and, an oxidizing agent in the form of the manganese. So we're able to get through a lot of that. So let's take a look at how this is better of a synthesis. Of course, first off, we have all of the atoms are incorporated into product. That's the atom economy. And the ones that aren't incorporated into the product are made back into the starting material. So we're okay with that. It's recycled. We see in the red ones here, the circled red ones, those are all things that are not incorporated into our final structure. Those are all extra atoms that we're going to have to deal with some other way. And so that is not economical in terms of atoms. Notice we're also minimizing. We remove the need for sulfuric acid. That's just going to be safer chemistry. Overall, this is going to be just kind of a designed, what did we say, less hazardous synthesis. Overall, the big thing here, of course, is the atom economy. We're still going to end up having our same amount of derivatives here. We're still going to have our intermediates. So that's unchanged here. But we're going to see that overall, this is going to be just kind of a better solution because we can recycle all of these extra atoms. So that's kind of our biggest benefit to making this happy product. This is our product, by the way, the one that we're looking to make. That's going to be our ideal, our product there, and so we're making it happily. What else do we have? What can we do with this? Of course, there would be some sort of catalyst used to get this to happen back again, which can be reused. So we have some catalysis going on here. Notice that the iron and all that are not actually catalysts because they are, in fact, used up in the course of the reaction. And so technically, if we want to even think about our starting material as a catalyst, we could if we carry on these reactions. So we're good with that. What else do we have with this? Just overall safer. But more importantly, here's our atom economy example. And we're just reducing the waste. Because we presumably have no waste products aside from, just undesired side reactions, which may happen. So overall, we have a lot of good things about this kind of second process. Any questions on that one? Alrighty, so last thing here is potentially, do we have oxygen coming out of this? We're oxidizing that side. Actually, all of the hydrogen peroxide gets incorporated into these two molecules, so we do not have oxygen as a byproduct here. From at least what I'm just very quickly looking at this. And even so, like stuff like that, like we produce water in this first one, we don't really care about that. Like that's fine. We can produce water. It's more ones that are toxic. So even if we do produce oxygen, that's all right. We're okay producing oxygen as a byproduct. Yeah, because it looks like both oxygens do get combined into these two molecules. So looks like we shouldn't get oxygen there. However, we would get we would probably get water out of this second reaction. Just whatever catalytic stuff we need to put in there, probably some catalytic acid. We would probably end up with some water out. So not toxic waste. Okay, so safe solvents. We want to avoid halogenated solvents. We want to avoid corrosive ones too. These are kind of two main ideas here. And then, of course, we want to avoid explosive ones. And so, unfortunately, most solvents fit into these three categories. We have a couple, namely this guy is an excellent solvent for avoiding these things. It is not halogenated, it is not corrosive, it is not explosive either. But we're going to see that water is superpolar. A lot of organic things are not polar. And so there is a pretty useful solvent that is neither explosive, corrosive, or halogenated, which is carbon dioxide in the supercritical state. If we remember way back when we talked about kind of phase diagrams, I don't know, something like this, where we saw that above a certain temperature and pressure, we could get behaving both as kind of a gas and a liquid simultaneously. And for carbon dioxide, it's actually pretty low. Let's look up its supercritical CO2. Let's see what its kind of triple point is, or critical point rather. Let's see. Okay, so its critical temperature is 304 Kelvin and 72.8 atmospheres. So above these two, carbon dioxide becomes a supercritical fluid. 78 or 72 atmospheres is not that big, chemistry speaking. A lot of glassware and reactors can handle hundreds of atmospheres of pressure, so 72 is not terrible. And what's great about using carbon dioxide is if you can get it into the supercritical state, it can act as a great solvent. It'll dissolve things. And so it'll have that kind of liquid capability of dissolving things, but still have the viscosity of a gas where it moves very easily. And so it works really, really nicely as a solvent. And better yet, in order to make it, all you do is pressurize and heat up some carbon dioxide, which we can just extract from the atmosphere very easily. And if you were to spill that solvent, all that would happen is you would release that same CO2. So we're having a net zero CO2 use by doing this, depending, of course, how we're generating this pressure and temperature. But all the CO2 we use just is already taken from the atmosphere. So if it gets released back into the atmosphere, there's no problem with that. And so we can kind of have this kind of excellent way of having a completely non-polar solvent that we can use to work with these things. And we're going to see that it can also be used to separate compounds from each other in what's called high-performance liquid chromatography. You can use supercritical fluids for that as well. So it's pretty cool stuff. So it's also a way of decaffeinating caffeine or decaffeinated coffee. It's a pretty cool thing. So coffee beans, have the caffeine in them. Rather than using horribly halogenated solvents, you can use supercritical CO2 to dissolve the caffeine and just extract it that way and then just blow off the CO2 later. It can be used for dry cleaning. So instead of using various halogenated solvents, which are used in dry cleaning like dichloromethane. You can use supercritical carbon dioxide to clean things. It's still dry because there's no water in it, but you also don't have these potentially very environmentally hazardous compounds being released. So, kind of a great green solvent there for your non-polar purposes. And you can use all sorts of other gases to put in a supercritical state, but CO2 is special in that it's relatively low for its critical point. So its properties for getting it to the supercritical state are not that difficult to achieve. And so as a result, it's an excellent kind of choice there. All right. So that's kind of one of the bigger green areas around. So is a solvent choice. So there we have it. There's also a little section at the end about click chemistry. It's just another example of atom economy. You can look at it if you like. I actually have done that particular reaction using an azide and alkyne. Back when I was doing research as an undergrad at UC Santa Barbara, I was in a lab that did a lot of click chemistry. So this has been a flashback for me way back when I was an undergrad. So it's nice to see that sort of reaction is finally in a textbook now. So pretty cool. So with that, we're done with environmental chemistry. So we have concluded the human suck portion of the course. Since I don't have practice exam questions for this topic, just focus on your homework problems as potential exam, similar to exam questions. How I plan to do this is your equilibrium will probably be 5 questions, and then your 6th question will be environmental chemistry, just because this stuff is not really new chemistry, as it were. It's kind of just a new way of looking at it and analyzing byproducts and that sort of thing. So it's more, if you want, you can completely forget this chapter and focus entirely on 16 and 17. Though I want to say the environmental one is pretty easy, chemistry-wise. So, up to you. So, you'll have 5 questions coming from 16 and 17 dealing with acid-base and then extra equilibrium. And then 1 question on the environmental chemistry. You'll choose 5 to answer just like before, so you'll be able to do that. It'll be the same format as before, so if I am caught lying to you, just let me know on Discord. I'll try and solve that as soon as I can. I'll be taking the exam as well with you guys, so I'll see if there's any errors as I go through it. So we'll be hopefully good there. Alrighty. Just so we also know, I am going to be getting my COVID vaccine today. So I do plan to have a review session tomorrow if you like. But I may be dead in that kind of like COVID vaccine side effect fugue state where I'll be like, very tired and all that. So I may have to, yes, thank you. I may need to postpone this. Maybe we'll do it on Friday or something instead. Just depends. So if there are questions that you'd like to go over or topics you'd like to go over, still put those in Discord. I'll plan to do those tomorrow if you want. Same thing with honors, by the way. I may postpone that or may just have you submit it as a written assignment instead of presenting it. And just depends. So we'll see. So I'll let you guys know in Discord tomorrow morning what's going to happen with that. But for now, let's plan on business as usual. So we'll plan on doing a review session tomorrow if you like. And we can go over whatever you guys would like to go over. All right, so exciting stuff. With that, I'll potentially see you tomorrow, or we'll figure something else out, and then we'll go from there. So enjoy your weekend. Your homework is due Saturday, don't forget. Both of them are due Saturday. I'll have the keys up for you on Sunday so you can review those, and then Monday will be the exam. So same thing as last time. So, all right. With that, happy studying, good luck, have a nice weekend, and maybe see you tomorrow, maybe see you Tuesday then. Or some point in between. All right, and I'm going to get these up before I forget this time. Okay, there we go. Hooray! All right, that one you see earlier is yesterday's, and then today's here is at 11. So, alrighty, take care, everyone.